Good day to everyone. I am John Vincent Ramis, and today, me and my partner, Juliana Martinez, will be presenting the group 15 and 16 elements. So let's start with the group 15 elements. These are known as the nitrogen family or pnictogens. The word pnictogens derives from the Greek word nigein, which means to choke. This refers to the choking property of nitrogen. The group 15 elements consists of nitrogen, phosphorus, arsenic, antimony, bismuth, and the new recently discovered moscovium. The elements found in this group share almost the same features of the electron configuration in their atoms. Next is their history of discovery. Firstly, arsenic has been a main component used by the ancient Greeks and was discovered by Albertus Magnus in the 13th century. Then came phosphorus. It was discovered by alchemist Henning Brandt in 1669 while on pursuit for the discovery of the philosopher's stone. Then, antimony was first discovered in 3000 BC, but it wasn't until 1707 where it was scientifically studied and recognized by French chemist Nicolas Lemery. In 1753, bismuth was discovered by Claude Joffre, and in 1772, nitrogen was first discovered by Scottish physician Daniel Rutherford. Finally, in 2003, moscovium was discovered after bombarding the atom with americium-243 with calcium-48. Now, let's discuss the general properties. All pnictogens have the electron configuration of ns2 and p3 in their outer shell. The nitrogen family is found in the p block, and it increases its metallic character as it moves down the column. Majority of the nitrogen family are covalent compounds. Now for its individual properties. Nitrogen is a colorless, odorless, and tasteless nonmetal gas. It has 5 electrons in its outer shell and is commonly used in fertilizers. Nitrogen also makes up 78% of the Earth's atmosphere. For phosphorus, it glows in the dark and has 3 colors of red, white, and black. It is a non-metallic solid and is highly reactive. It is commonly found and used in toothpastes. Then arsenic. It has 3 allotropic forms: arsenic yellow, black, and gray. It tarnishes rapidly in the air, and at room temperature, it exists as a metal with brittle characteristics. These are commonly used in wood preservations. Antimony is a semi-metallic chemical that exists in 2 forms: metallic and non-metallic. It is a poor conductor of heat and electricity, but it is stable in dry air. It is an important metal. Bismuth is a white crystalline brittle metal. It is the most diamagnetic metal and is the second metal that has the lowest thermal conductivity, only preceded by mercury. It is stable in oxygen and water and is sometimes used in shotguns. Moscovium, unlike the rest, is an artificially produced radioactive element which has the physical properties of a heavy metal. Now, let's discuss the reactivity of the group 15 elements. As you move down the group, the density, atomic, and ionic radius increases, while the ionization energy and electronegativity decreases. The compounds tend to be stable and potentially toxic due to the atoms forming double and triple bonds. Nitrogen and phosphorus behave chemically like nonmetals, while arsenic and antimony behave like semimetals, and bismuth and moscovium behave like metals. The reactivity of the pnictogens decrease as their atomic number increases. Finally, here are a few recent researches on each of the elements. For nitrogen, a study done in March of 2019 revealed that nitrogen is being produced from a relationship between an alga and bacteria in the Arctic Ocean. The organism phytoplankton was always limited in the amount of carbon it can remove in the upper ocean and atmosphere without nitrogen. But now, with a new source offered by the UCYN-A, phytoplanktons could be more productive, which ultimately decreases the atmospheric carbon levels. Then, for phosphorus, fertilizer use has impacts on the environment. Although it helps boost plant growth and increases production of crops, overusing these can cause negative environment issues. Thus, JRC scientists assessed its physical and chemical status in Europe's soils and determined that phosphorus can be used as an alternative for fertilizers. It is both beneficial to the environment and economy of Europe. Next, arsenic. A study done in October 2020 found that drinking water is now contaminated with arsenic and is one of the major health issues in 50 countries worldwide. This contamination increases as new reports come in from all around the globe, and it was found that the element is mobilized into the environment through natural ways such as volcanic activities and weathering. One of the solutions to this problem is inducing an arsenic-safe diet. Acarus calamus, also known as sweet flag, is a flowering plant with psychoactive chemicals. Researchers in China conducted an experiment of exposing its photosynthetic pigment to antimony potassium tartrate to serve as a remediation plant. Because antimony can be absorbed by plants in the soil, sweet flag was tested on to see if it can enhance its growth and photosynthetic efficiency. For bismuth, its complexity has been widely used in the field of medicine over the years, and researchers have further studied on this subject and determined that the application of bismuth compounds have the potential to become anti-cancer drugs. For moscovium, because it is an artificial element and was just recently discovered in 2003 with its formal recognition in 2015, moscovium has yet to have new studies behind its uses and properties. Next, to discuss the group 16 elements is my partner Juliana Martinez.
So now we have the group 16 elements, which is also called the chalcogens or oxygen group. Group 16 elements are considered to be part of the main group elements. It consists of the elements found in group 16 of the periodic table, which are oxygen, sulfur, selenium, tellurium, polonium, and livermorium. These elements are closely related to life. Just imagine a life without any oxygen. Living organisms simply cannot live and survive life without the appropriate amount of O2 in one's lifetime. Moreover, sulfur is responsible for the structure of certain proteins in all living creatures. These are just some of the incredible uses of group 16 in our life. Let us first dwell on their history and who discovered such elements. Oxygen was discovered during the year of 1774 by an English chemist named Joseph Priestley. Sulfur was discovered sometime around 1777. It was Antoine Lavoisier who persuaded most of the scientific community concerning sulfur. Selenium was discovered by a Swedish chemist, Hans Jacob Berzelius, in 1817, while tellurium was discovered in 1783 by Franz Joseph Müller von Reichenstein. In 1898, it was Marie Curie and Marie Curie who discovered polonium, which was named after Poland, the homeland of Marie Curie. The sixth element of the chalcogens group is livermorium. It was discovered during 2000 by scientists from the Joint Institute for Nuclear Research in Russia and the Lawrence Livermore National Laboratory in California. For the different properties of group 16 elements, let us first start off with oxygen. Oxygen is a gas at room temperature and at 1 atmospheric pressure. It is colorless, odorless, and tasteless. Furthermore, oxygen has two allotropes, which are O2 and O3. Allotropes are each of the two or more physical forms that an element can have. Sulfur is a solid at room temperature and just like oxygen at 1 atmospheric pressure. Moreover, sulfur exists naturally in a variety of forms, including the known elemental sulfur, as sulfides, sulfates, and organosulfur compounds. Selenium appears as a red or black amorphous solid, or a red or gray crystalline structure. The latter, or having the red or gray crystalline structure, is the most stable one. Selenium has proteins very similar to those of sulfur. However, it is more metallic, though it is still classifying as a non-metal. Tellurium is the metalloid of the oxygen family, with a silvery white color and a metallic luster, like tin at room temperature. Additionally, tellurium is a very rare element that is most usually found as a gold telluride. Polonium is very rare, radioactive metal. There are 33 different isotopes of the element, and all the isotopes are radioactive, which means it is absorbing ionizing radiation or particles or connected to the emission of ionizing radiation or particulate matter. It exists in a variety of states and has two metallic allotropes, which are the alpha form and the beta form. Both are stable at room temperature and have metallic characteristics. For the last element of the group 16, we have livermorium. It is a highly radioactive metal. Due to its position within the periodic table, it is expected to have properties similar to polonium and tellurium. For the general properties or trends of the group 16 elements, firstly, the metallic properties increase in the order oxygen, sulfur, selenium, tellurium, and polonium. Secondly, the electronegativity, ionization energy, and electron affinity decrease as atomic weight increases. With that, we can say that there is an inverse relationship between the atomic weight and the electronegativity, ionization energy, and electron affinity. Thirdly, the melting point, boiling point, density, atomic radii, and ionic radius increase from down the group, which means from up to down. Oxygen having the lowest melting and boiling point and the smallest atomic radius and ionic radius, while livermorium having the largest atomic radius and having the highest melting point and boiling point. Lastly, elements within group 16 commonly have negative 2 as its oxidation state. However, sulfur can exist at plus 4 and plus 6 state, and it is possible for selenium, tellurium, and polonium to exist at plus 2, plus 4, and plus 6 states. The reactivity of elements in group 16 decreased from lightest to heaviest, just like in group 15. Selenium and tellurium, for example, react with most elements, but not as rapidly as sulfur. Sulfur, selenium, and tellurium do not always react with water, aqueous acid, or aqueous base, as nonmetals do, although they do dissolve in highly oxidizing acids like HNO3 to generate oxoacids like H2SO4. Polonium operates like a metal, dissolving in dilute HCl to generate solutions containing the PO2 plus ion, unlike other chalcogens. An example of the reactivity within group 16 elements is when chalcogens react with dihydrogen, and it usually forms hydrides, with the general formula H2X, where X is any of the 6 chalcogen elements, which are oxygen, sulfur, selenium, tellurium, polonium, or livermorium. This is the chemical formula for this kind of reaction. X, which is a chalcogen, plus H2, a dihydrogen, yields H2X, which is the hydride form of the chalcogen. One of the recent research involving oxygen is the oxygen therapy. Due to the ongoing COVID-19 pandemic, many are suffering from hypoxia. It is a life-threatening condition in which the body's tissues lack oxygen. According to a new study in the journal Stem Cell by a group of researchers from the University of Alberta, the findings also explain why the anti-inflammatory medicine dexamethasone has shown to be a successful treatment for patients infected with the virus. Researchers from the University of Liverpool are achieving substantial development in their effort to generate new sulfur polymers that can replace harmful petrochemical-based plastics. A new way to decrease environmental impacts to have sustainable life on Earth is the latest research about sulfur. For element number 34, selenium, there is a study about the connections between selenium, selenoproteins, and the thyroid glands. Human health is being linked to selenium as the findings shows that the isotopic element selenium is a necessary micronutrient for the formation of selenoproteins. The thyroid gland expresses the majority of unknown selenoprotein. Nutritional supply regulates selenium levels in selenium-sensitive tissues such as the liver, kidneys, and the muscle, as well as activation of non-essential selenoproteins like the glutathione peroxidases. For tellurium, as times and technology are changing fast, wearable technology demands both durability and flexibility. A new nanowire model, a boron nitride nanotube, packed with tellurium atomic chains, shows promise for light-triggered and pressure-triggered electronics. The new nanowire has now been constructed and tested alongside with carbon nanotubes by physicists. Some polonium isotopes have a high alpha emission rate, making them a lightweight and portable energy source. As a result, polonium-210 is a viable source of energy for spacecrafts and satellites with limited capacity and mass. Polonium-238 has traditionally been employed as a power source in a space exploration, but other isotopes such as polonium-210 have also been studied. There is also a study regarding combining a polonium source with a thermoelectric cell to power aircrafts. When livermorium nanoparticles are exposed to ultraviolet light, some of the light is dispersed while the rest is being absorbed. The quantity of energy dissipated in a non-emission process is mostly determined by the material and volume of nanoparticles that can be measured using the absorption cross-section. Thermoplasmonic properties of livermorium nanoparticles with spherical, core shell, and rod geometries are examined in this study.